Right, given the video has probably started recording by now, I think I can make this announcement. I just want to draw your attention to the fact that this time, in 2 weeks' time, you'll be doing a quiz here in this room, okay? There are a few people that won't be in this room. I'll be emailing them separately because currently we still have slightly more people than fit into this room in the class. And I'm assuming we'll have a big attendance this time in 2 weeks' time. Okay, did you all see this announcement yesterday? Good. Any questions about it? Okay, so just want to emphasize, this time in 2 weeks, quiz here. It's a 45-minute quiz, 15 multi-choice questions, closed book. Don't really have the space to bring your books along anyway. What else is there to know about it? It covers everything up to and including all of last week, and there's a little bit at the end of today's lecture that's also included because it's part of lecture 5 on flip-flops. But we'll start on lecture 6 first. So, without further ado, let's do that. So this lecture is about synchronous sequential circuits. Okay, it's a bit of a mouthful. What we're going to learn about are design techniques for circuits that make use of flip-flops and understand the concept of states and their implementation with those flip-flops. We're going to learn about the synchronous control of circuits using a clock signal and hence the synchronous sequential circuits. We'll learn how to design synchronous sequential circuits, learn how to specify them using VHDL, and understand the techniques that CAD tools use to synthesize synchronous sequential circuits. We won't be looking at asynchronous sequential circuits, so there's a whole other class of circuits called asynchronous sequential circuits. They require far more design techniques than we can cover in this course, and so they are very much an advanced topic. We won't be talking about them here. So, so far we've looked at combinational circuits where the output of the circuit is directly dependent upon the present or current input, right? That's what a Boolean function does. These are functions where the output is a direct functional combination of the inputs. We've also, last week, looked at flip-flops, whose outputs are defined by their current state. So in this class, or in this lecture, we're going to talk about a class of circuits that are known as sequential circuits that, where the outputs depend upon the past inputs and the current state as well as the present input to the circuit. We normally use a clock signal to control those circuits, and that's why they're called synchronous sequential circuits. And so clearly we're going to be combining what we've learnt so far to build circuits that involve both combinational logic as well as flip-flops. And this is really at the core of designing control circuits, or digital controllers, if you like, which are going to be very important when we talk about digital circuits in general, where we need some sort of controller to control the operation of the system. Okay, this is a really nice general model of a sequential circuit. You can think of it as comprising some combinational circuit that takes the inputs as well as the present state of the circuit, which is given by the state of the flip-flops, to produce the next state that the flip-flops should have, and some combinational circuit that depends upon the present state, which produces the outputs. Okay? So the important thing to note is that changes in state, the current state of the flip-flops, depend not just on the present inputs, but also on the present state of the flip-flops. We may also have a feed-forward network, if you like, between the inputs that makes the outputs dependent upon not just the current state, but also the current inputs. But that may or may not be present. It's not required that it be present. Okay? In fact, those circuits where it's not present, where this feed-forward path between the inputs and the output circuitry is not present, where the output is only a function of the present state, they're known as Moore-type sequential circuits. Okay? If that feed-forward path is present, then this is known where the current output is a function not just of the present state, but of the current inputs as well, then that's known as a Mealy-type circuit. Okay? Maybe an easy way to remember the difference between the two is that Mealy is a slightly more complicated word than Moore, and you can think of, adding this feed-forward path in there as adding a bit more complexity to the circuit. So the Moore is the more simple case where the current state is only the outputs are only a function of the current state. The Mealy is a bit more complex in that it allows the output to also be a function of the current inputs. Okay, the functional behavior of a circuit is defined by this set of flip-flops. Obviously, for any circuit that we build, there's a fixed number of flip-flops there, and therefore there's a finite number of states that this circuit can have. And hence another name that's given to this general class, these synchronous sequential circuits, is to call them finite state machines. Right, so we're going to get straight into having a look at a very extended example. We'll be talking about this example for at least the next half hour and looking at various incarnations of it. And we'll be learning techniques for how to design finite state machines or synchronous sequential circuits on the basis of this example. So the specification is that the circuit has a single input W and a single output Z. That the output Z is 1 if in the two immediately preceding clock cycles, the input W was 1. If the input in the immediately preceding two clock cycles was not 1, then the output is 0, as Z is 0. And finally, that all changes in the circuit occur on the positive edge of a clock signal. Okay? So here's an example of the input-output behavior that we're expecting for this circuit. We can see here the input W over a number of clock periods, 0 through 10. We see that after two successive clock periods, T3 and T4, where the input is 1, in T5 we see the output Z going to 1. We also observe that it goes back to 0 because there's a 0 read in the immediately preceding clock period, T5. But after T6 and T7, we see the output going back to 1. And because there's also 1 in T8, the preceding periods T7 and T8 force a 1 in the output in period T9. Okay? Are there any questions about the behavior of the circuit here? Good-o. So, we call a circuit that recognizes a particular input pattern a sequence detector. That's also another generic sort of name. It's not particularly important or anything like that. It's just a common digital control function that we need to perform. Is to recognize some particular sequence of events occurring. Okay, I think this slide primarily tries to convince you that it's not possible to design a purely combinational circuit that would perform this function, because we can see that in periods T2 and T5 we have a 0 as the input, a 0 is the output in T2 and a 1 is the output in T5. And I think there's other examples such as T4 and T8, let's say, where we have a 1 as the input in both cases, but there's a 0 as the output in T4 and a 1 as the output in T8. So clearly a combinational circuit isn't going to perform the sort of function, the behavior that we want the circuit to exhibit. And this implies also that the output has to be a function not just of the present input, but also some previous inputs into the circuit and potentially the state that gives rise to. So the first step that we have to make if we're going to design a finite state machine is figure out how many states do we need to have in our machine. How many states does our machine have? So unfortunately, there's no good general algorithm for figuring that out. You really need to use your own intuition and understanding of the specification to figure this out. But in our particular machine, it's not too difficult to appreciate how that comes about, and it shows you how you would, in general, perform this procedure. So we're going to select a starting state that the circuit must be put into when it gets reset or started. We're going to just call that state A. And in that state, we need to consider, well, what inputs can we observe in that state, and what should be the circuit's response as a consequence of this. So we know that for our design, we're only interested in recognizing 2 1s in a row, right? So if we get a 0 as an input, that's really not an interesting input to the machine. So the system should stay in this state A in that case. But if a 1 is observed, then the circuit has to somehow remember that we've seen a 1. And the best way of doing that is to define a second state B, which basically says we've just seen a 1 in the previous clock cycle, right? And it would make that transition when the next positive clock edge comes along after that W is 1 is seen, right? So we go through the same sort of analysis in this state. So given that the circuit is now in this state B where we've seen 1 1, consider what the circuit's response or the circuit's behavior for every possible input in that state. Well, if we get a 0 in state B, that's again not interesting. In fact, it's a reset condition because now we've just seen a 0 in the previous state. We haven't even seen 1 1. So what we should be doing is going back into state A in that case, right? And doing that on the next positive clock edge. But if we see a 1 instead, then we have to distinguish that from state B, because if we see a second 1 in a row, the one that led us into state B, and a second 1, then we want to know that that's the accepting case where we've just seen 2 1s in a row, and therefore we can define or can rationalize, can realize there has to be a third state in this system where we effectively which effectively denotes the fact that we've just seen two successive ones in the previous two states. So if in state B we receive a 1, we should enter a third state, an accepting state, where the output Z becomes 1, and this state denotes that we've seen two 1s in a row in the previous 2 clock cycles. We're not done yet though, because in this state we have to consider again what should the circuit's response be for each possible input. If we get a 0, what do you think we should do once we're in state C, when we're in state C? Sounds like a good idea. It's of no interest to us. It essentially resets the pattern and indicates we've only seen a 0 in the previous state. There hasn't been 1, 1, 1 seen in the previous state. So if we get W is 0 in state C, we should return to state A, right? But if we get a 1 in state C which says, well, which really denotes the fact that we've seen two 1s in a row in the previous 2 clock cycles, if we get a 1 in this state, then we should stay in this state, because basically it's still true that we've seen two 1s in a row in the previous 2 clock cycles, right? So while we receive a 1, we stay in state C. We've now considered all possible inputs in these 3 states. So the system is closed. There's no more new state that any possible input gives rise to. So we can conclude that 3 states is enough to define this finite state machine. Okay? Are there any questions about this analysis that we just did? Okay, so great. So we know we've got 3 states. How do we formalize this and help use that information to help us design a finite state machine? So the first step that we would take is to draft what's known as a state diagram, which really shows us what the behavior of this finite state machine should be. In fact, the analysis we just did is usually carried out through the construction of this state diagram. So a state diagram is just a directed graph that comprises nodes that represent the states of the system and directed edges which indicate the transitions that should take place between states on particular inputs. For our particular design, this is the state diagram that results. We see that our reset state takes us into state A. In state A, we have not seen two 1s in the previous 2 cycles, hence the output Z has to be 0 in this state. And we determined previously that if we get 0 as an input in state A, we stay in state A. On the other hand, if we see a 1 in state A, then we were to enter a state B, which signifies that we've seen a 1 in the previous clock cycle, right? And this transition is meant to happen on the active clock edge, positive clock edge in this particular case. Note that the transition is labelled with the situation that W is 1. Since in state B we've only seen 1 1 so far, the output should still be 0, right? And hence we label the state with that fact. And again, go through our analysis. What happens if we get a 0? What happens if we get a 1? Well, in state B, if we got a 0, we determined we should go back to state A. And if we got a 1, well, then we want to go to a third state that recognizes the fact that we've seen 2 1s in the preceding 2 clock cycles. So this is our state C, where that fact is now known, and therefore our output should go to 1 in state C. We also determined that if we get another 1 in state C, then we should stay in state C because it's still true that the preceding 2 clock cycles had a 1 as an input. On the other hand, if we see a 0 in state C, we return to state A. So that's the state diagram that we would have derived if we'd gone through this analysis and built the sort of behavioral description of the circuit as we went along. All right. This note, essentially, I mean, it's not special that we called these states A, B, and C. We could have given them more meaningful names, so that's really immaterial. What is relevant is that we label the transitions with the input that causes that state transition, and that conceptually, that transition is taken when the active clock edge comes along. All right? Okay, so we have our state diagram, but that doesn't help us really program a computer or configure an FPGA. So we have to do some further processing. And the first step usually is to convert this state diagram that we've derived into something that's known as a state table, which is, there's a one-to-one mapping between these two, I hope you can see. The table simply lists what the present states are, all possible states, and what the next state would be based on all possible inputs, and finally what the output should be for that present state. Okay? And that's a step towards having sort of a systematic analysis, which then allows us to implement a circuit. But to do that, we really have to figure out, well, how many flip-flops do we need? And usually those flip-flops are associated one-to-one with what's known as a state variable. These state variables are the variables that will carry the state for our diagram. So in our particular case, we have 3 states. So in order to uniquely identify those 3 states, we'd need at least 2 state variables to represent them in a binary system, right? So we have our state variables, which give rise to the next state of the flip-flops, and the present state of the flip-flops is given by the lowercase version of these state variables, and they're then what determine what the next state should be based on the next state logic, and also what the output of the system should be based on the output logic. All right? So conceptually, we know that if we've got 3 states, we need 2 state variables, therefore we've got to have 2 flip-flops. But how are we going to label the states, or how are we going to associate a particular valuation of these state variables with each of the states, the symbolic states that we had previously identified? We had A, B, C. We now have to turn that into a valuation of these particular state variables. So the next step really is to derive from the state table a so-called state assigned table, which associates a particular valuation of these state variables that we have with each of the states. And then it's again just a one-to-one mapping between the two. So here we're using a binary numbering system to label the states A, B, and C. A is given the number 0, 0, B 0, 1, and C 1, 0. And since we've got, for 2 state variables, a 4th possibility, 1, 1, well, that's going to be added to our state table, and we won't care what the next state really is if we ever enter this state, because in principle, we will never enter that state. We'll design it so that we'll never enter that state. And the rest is just a direct translation. Wherever A appears, we write 0, 0. And wherever B appears, we write 0, 1. And where C appears, we write 1, 0. Okay? But now we have all that we need to determine how the next state variable valuations are determined based on the present state and the input. Okay? So that analysis is done here. So once we have this state assigned table, that allows us to figure out, well, what are the logic equations that connect the state variables, the next state values for the state variables, with the present state values for the state variables and the inputs. Okay? So let's just focus on the left side here where we ignore the don't cares that are down here. So we're just really focusing on the first 3 lines of this table. Okay? In that case, when is y1, capital Y1, which is the next state variable, remember from our model, these are the next state variables that we're trying to define. And we're trying to figure out what is this next state logic that has to go in here. Okay? And that is purely a function of the input and the present state, right? The present state being given by the lowercase state variables. All right, so when is capital Y1 1? Well, it's only 1 in this very first row, and when W is 1. That is, when we have W and not Y2 and not Y1. So that's the logic equation that we can immediately derive for capital Y1. What about capital Y2? Well, capital Y2 is 1 in these 2 rows where we have an exclusive OR of Y2 and Y1, and when W is 1, not when W is 0. Okay, so we have W and not Y2, Y1, or W, Y2, and not Y1. Okay, that's the exclusive OR of those 2 state variables and W. And finally, when is Z1? Well, it's only 1 when the present state is Y2, not Y1. So that's what we see down here. When we have don't cares, that gives us additional opportunities to simplify these expressions. Unfortunately, as you can see when you lay this table out in Carnot maps, we can't combine the 1 for capital Y1 with any of the D's here because they're not adjacent. So that doesn't allow us to simplify the expression for the next state variable for Y1. However, for Y2, we can combine both of the ones that we saw previously, the exclusive OR columns, with the D that sits between them, thereby simplifying. So we can see that this is W and, well, Y1 is 1 in both of these cells, and in both of these cells, Y2 is 1. So obviously there's a simplification that we can perform there. And as for Z, it can also be combined with the D below so that it becomes just Y2 rather than Y2, not Y1. All right? So I hope you can see how using the don't cares can make life a little bit easier, can lead to simpler expressions. So the circuit that results is as is depicted here. We have here our 2 state variables given by the flip-flops, Y1 and Y2. We know that the expression for Y1 is W and not Y2 and not Y1. So here's W coming in, and we have a not Y2 coming in and not Y1 coming into this AND gate. So that provides capital Y1. And capital Y2 is given by, again, W and either Y2, sorry, or Y1 coming in via this OR gate up the top. And finally, the output logic Z is 1 when Y2 is asserted. This is purely just an implementation of the equations that we've derived, which was based on the assumption that we use D-type flip-flops to implement the logic. D-type flip-flops are always preferred because preferred over T-type flip-flops or JK flip-flops or SR flip-flops because there's a direct relationship between the input and the next state, the next output state, right? You don't have to do any more figuring out there. There's no indirect connection between the input and the output state. Does this circuit look right? Does it look like it would do what we want it to do? Well, assuming we're reset, with W is 0, both of these AND gates are not going to have any impact, and so the circuit's going to stay in the state 0, 0, right? But if we do get a 1, so then this AND gate is going to have an active output because the not Y2 and the not Y1 are both going to be 1, so there's going to be 3 1 inputs to this AND gate, and therefore capital Y1 is going to be 1, right? As for the upper input, well, neither Y2 nor Y1 are 1 when we first see our first 1, because the state of the flip-flops is going to be 0, 0, and therefore the input to the top flip-flop is still going to be 0. So we will move with the first W from the state 0, 0 to the state 0, 1. If we see a subsequent 0, that's again going to drive this AND gate to 0, and therefore this guy is going to be driven with a 0, and we'll revert back to the state 0, 0 from 0, 1 if we get a 0, right? But if we do get a 1 in the state 0, 1, then this lower AND gate is going to have, well, a 0 coming into it from this flip-flop, while it still has a 1 coming in from this flip-flop. So we'll have a 0, drive a 0 onto Y1, capital Y1. So this flip-flop will change from 1 to 0. The upper flip-flop will change, well, given that we have W is 1, given that lowercase y1 is 1, then this guy is going to be driving the next state, capital Y2, to 1, and therefore the upper flip-flop will go to 1. So we will go from the state 0, 1 to the state 1, 0 if we see a second W. Perhaps that's easier to appreciate by having a look at the timing diagram that was implied by our initial specification of the circuit. If we think of these time periods as spanning both the positive and the negative half of a clock period, so defined by these grey vertical bars, they define the clock periods that we see. Then we see at the end of the first clock period here that W is 1, right? While Y1 and Y2 are both 0. But given that we get a rising clock edge when W is 1, that forces the output of the lower flip-flop to 1. So we're now in that state 0, 1. On the next positive clock edge, however, W is 0, and therefore the state of the lower flip-flop is changed again to become a 0. On the subsequent rising clock edge that we get at the beginning of period T4, W is 1, therefore we'll see on that rising clock edge again the state 0, 1 appearing. In the next clock period we still see W as 1, and given that that coincides with Y1 being 1, due to the logic that we have up here, that's going to drive this upper flip-flop to be 1 and the lower flip-flop back to be 0. So when we have the upper flip-flop being 1, of course, our output Z goes to 1 as well. But on the next rising clock edge, W is 0 again, and therefore the whole system resets. We go back to a state of 0, 0, the output being 0. And on the next rising clock edge, we see that W is 1 again. So again, we go into the state 0, 1. we see a second 1 and therefore go into the state 1, 0 with the output being 1. We see a third W, which is really just recycling the Y2 being 1 now up the top here. So we stay in that state 1, 0, 1 and 0. And we see that our output stays high. But on the next clock edge, we see that the input W is low, and therefore the whole system resets itself again. I hope that's clear, but are there any questions about it? Good, good, good. All right. Am I going too slowly? No? You're happy with the pace. Okay, good. So let's just summarize what we've done. We've just designed our first finite state machine. Happens to be a Moore type circuit because the output here is a direct function of the current state. Z is Y2. No influence from the input at this stage. All right? So we obtained the specification. We derived the number of states by using a state diagram to chart out what possible states we have under all possible input conditions, and we kept elaborating that diagram until it was closed. There's no more possibility of expanding it, right? We then created a state table from that diagram, which is just tabulating the design of the state diagram. The number of states that we have in our system determine how many state variables we have to have, namely how many flip-flops we must have, right? If it's 4 states, 2 is enough. If we have 5 states, how many do we need? How many state variables if we have 5 states? Why? Two will only allow us to distinguish 4 states. We need a third flip-flop or a third variable to distinguish 5 to 8 states, right? And so on. So it's really just the log base 2 of how many states we have, the ceiling of the log base 2 of how many states that we have, that tells us how many state variables we need, right? We then perform a state assignment, which in our case we just did arbitrarily. And then based on the type of flip-flops that we're using, we determine what the next state table should be, what the state variables, what the next state logic needs to be, and what equations we need to drive those next state variables to the desired output. And finally, we implemented the circuit. And if you were doing things properly, you'd want to simulate your design and then test it out on the board to make sure that it's working properly, right? All good so far? Right. So I have a question. We just arbitrarily chose the state assignment. Is it possible to get, are some assignments better than others? Because that was sort of one of the undefined or left unanswered sort of questions. What was the best way to make that assignment? And so it raises the question, is it possible to obtain better implementations for different assignments? And the answer to that is yes, it is. You should already have been suspicious about that. For example, this was our state diagram. We then had our state table, but we made the assignment of 1, 0, the valuation 1, 0 to state C. If instead we make state C 1, 1 and leave the valuation 1, 0, the state variable valuation 1, 0 to be the don't care condition, then that gives us much more opportunity to optimize the logic for our next state derivation. We can then see that for capital Y1, it's 1 in every row when W is 1. So the only thing that matters is that W is 1 to determine capital Y1. if we're implementing D-type flip-flops or using D-type flip-flops. And as for capital Y2, well, it's now true whenever lowercase y1 is 1 and w is 1. So if we have wy1, that's enough to describe the input for capital Y2, or how we derive the next state, y2. And as for the output, well, that seems to be, it could be defined to be 1 whenever lowercase y2, whenever the state variable y2 is 1. And so these equations are quite a bit simpler than the equations that we had previously. And so now all we need is one AND gate actually to operate our finite state machine. Obviously when W is 1 on the next active clock edge, lowercase y1 is going to go to 1, right? And as long as lowercase y1 is 1, if we get a second W when the next active clock edge comes along, this AND gate's going to be 1, and therefore the upper flip-flop's going to go to 1 as well, right? But if we get a 0 as the input, both the upper and the lower flip-flops are both going to be set to 0. Okay, so the same analysis can be applied to the timing diagram that we saw before. We see, for example, at this, the start of T4 on the rising clock edge, W is 1, therefore Y1 goes to 1. On the next rising clock edge, W is still high, and therefore we see Y2 going to 1 as well, and since Y2 is 1, Z is 1, right? But on the next rising clock edge, W is back to 0, so we clear both flip-flops and the output Z. Of course, you need to check that the system behaves correctly for a single W as well, not just two W's, and we also need to check, well, what happens if you get more than two W's in a row to make sure that it's all working correctly. Okay, so what we've analysed so far is the so-called Moore state machine, in which the output is purely dependent upon the current state. We also mentioned earlier that Mealy state machines provide additional flexibility in that we can use the current state as well to influence the output. And as a consequence, for the same behaviour that you would observe with the Moore machine, you can often get away with less states in a Mealy machine, and they're quicker. They've got a slightly more responsive behaviour. Let's see how that comes about. So in that example that we looked at, the specification required that the output be 1 in the cycle after 2 consecutive 1s had been seen. Well, what if we change that slightly and say that the output's allowed to be 1 in the cycle that we see the second 1? Okay? So then, effectively, the behavior that we saw previously changes in that the output Z is shifted by 1 clock cycle earlier. Now we see that the first one appears on the second one in time period T4. Previously, it went 1 in time period T5. We also observe that the output is 1 in time periods 7 and 8, corresponding with the second and third W that we see in a row. But as soon as we get a W 0 in T9, the output goes back to 0. So the impact of this change is that the output shifted forwards in time by 1 clock period. Okay? So if we go through our analysis again, then we have our reset state A. If in A we get a 0, we stay in state A, and the output should be 0, right? But if in state A we see a 1, then we're going to go to a state that acknowledges the fact we've seen a 1 in the previous clock period, right? Of course, we haven't seen 2 1s in a row yet, so the output should still be 0. But if we're in this state and we now see a 1, I don't know which one I did first. If we see a 0, obviously we've got to go back to state A because that's our reset state. But if we see a 1 in this state, well, then we know we've seen our second 1 in a row, right? Because we saw a 1 in the previous clock cycle. That's how we ended up being in state B. So a 1 in this state causes us to output that 1. And the spec allows that. The spec says, when you see that second 1 in a row, that's when you output Z is 1. So not only is our output being observed 1 period sooner than it was for the Moore machine, we also only have 2 states now, which means how many state variables do we need? Correct. We now only need 1 state variable. We've only got 2 states, so that means we can get away with just having 1 flip-flop. So this is going to be a smaller circuit, right? Why is smaller good? Why is smaller better? Faster. Something else. Cheaper. Something else. Less chance of failure. Very good. Is there a 4th reason? They're the ones that we've talked about in the class. There are probably many more that we're not. Oh, usually, you've got less hardware. What does that imply? Less power, right? Got to be cheaper to run as well. Okay. So the static power will go down. The dynamic power doesn't necessarily go down, but with 1 flip-flop versus 2, the dynamic power, the power that is consumed when the system changes state, has to go down because you're only changing state for half as many state variables as you would have been doing previously, right? So power is definitely less with this guy as well. Right. Only got 2 states, therefore only 1 state variable is required. Here's our state table that follows, but hang on. We now have to distinguish between what input we're using to determine what output, because here in state B, we output a 1 if we get our input of 1, and we output a 0 if our input is a 0, right? So in contrast to a Moore machine, where the output is only a function of the present state, for a Mealy machine, the output is a function not just of the present state, but of the current input as well. Right? Right. So we've got our state table. What's the next step? State assigned table. So we have our 1 variable, y. Without loss of generality, let's say state A is 0 and state B is 1, although could think of it the other way around. I don't think it's going to make any difference though. So since B is the state that's entered in when we have W equal to 1, obviously capital Y is just W, right? Because it's when W is 1. And as for the output, it's only 1 when we have W is 1 and we're in state B, which is Y. So we have W and Y for our output. So what does the circuit look like? Here, our single flip-flop with W as the input. And the output logic now takes not just the current state into account, but also the present input W into account. Right? When we analyze it then, here we've got W is 0, so no change in the state from 0. Rising clock edge at time period T2, we've got input W is 1, therefore the flip-flop goes to 1. But at that time, W is 0 again, or becomes 0 very quickly, and therefore Z is 0. And we return to Y is 0 on the next rising clock edge because W is 0. But then on the rising clock edge at time period T4, we see the input is 1, therefore we go into the state Y is 1. And a short while after that, given by the propagation delay of that AND gate, we'll see the output rising as well because W is still high here, right? And it will stay high until the next rising clock edge, at which point W is still 1. So the flip-flop stays in state 1 asserted, but when the output W goes low, when the input W goes low, our output goes low as well because this AND gate will switch off. Of course, that's some little delay behind the input going low. All right. Here we see then 3 successive ones in a row whereby the first rising clock edge gives rise to the flip-flop going to 1, then the output goes 1. The next rising clock edge, input still high, flip-flops high, output doesn't change. Next rising clock edge, input's high, the flip-flop's high for the next clock period, but the output goes low as soon as the input goes low. All right, so we've seen that it's more responsive, but there's also sort of a bit of asynchronous behavior here. This output is now dependent upon the input. Every time the input changes, even if there's no change in state, we could potentially see a change in the output. So that's something that has to be borne in mind. All right, and I think that that's probably a good point for us to have a 5-minute break. Yes? Yes. Yes, it is different. We defined it, or we required it to be different, and that's what gave rise to the Mealy design. Namely, what we said was, we want the output to be 1 during the clock period that W is high for a second clock period. So we changed the specification, and that gave rise to a shift forwards in time of the output. It moved forwards by 1 clock period. And basically, it behaves exactly as required. The only thing is there are slight lags now that we have to worry about in the output, or that might give some concern. But generally, we're only ever interested in what the output of the machine is when the active clock edge comes along. So when we get a rising clock edge. Okay, so the fact that this goes low halfway through the period doesn't really matter. What matters is it's low by the time the next positive clock edge comes along. Any other questions? All right. Any questions on labs? It's a bit disconcerting to see a fellow in the front row sleep here.
He's had a big afternoon.
Had a big afternoon.
Yeah.
It's only 1. So he's only had a big afternoon. You mean this afternoon? Yesterday afternoon. Right. So in the old days, what we used to do is fire a piece of chalk. Very few classrooms have pieces of chalk these days, so it's not that easy. You'd probably get sued for assault. There's no fun in the world. Not anymore. Well, there is, actually. You just have to watch Donald Trump. Ooh, I'd better turn this off. Just have to watch Donald Trump, right? bizarre sort of worrying joy that one has. Those last 15 minutes, they'll be in the exam, of course. Not getting a response. Any questions about anything? Quiz? Labs?
Is the quiz going to be, like how many questions are going to be on?
15?
And is it 1 hour?
45 minutes.
Will we have the hour lecture after? Or?
Yes,
Yes, okay.
probably. I don't know. Depends where we're at.
Okay.
Depends if there's more than a quorum sitting in the theatre after the paper.
It might be the one time we'll be able to get a full lecture.
Something tells me everybody will leave. Allowed a pen and paper. Yep. All right, let's continue on. Right, so we've now seen both Moore and Mealy versions of the circuit that we took upon ourselves to design. So how do we use CAD tools to design finite state machines? Well, we could just use structural VHDL. What does structural VHDL mean?
Writing out all the gates.
Or even the components and sort of wiring them together in a certain way that defines the structure, right? But manually designing them this way is not just tedious, it's error prone. So CAD tools offer better alternatives because it's pretty easy actually to implement finite state machines. There are graphical tools that can capture the state diagram and from there simply produce hardware description language. Or more commonly, you would use behavioral hardware description language to use to capture the diagram that you've derived. So we're going to have a look at how that's done with the 2-1s recognizer that we've been studying. So recall that this is the state diagram for the Moore version of the finite state machine. We have 3 states, A, B, and C. where state A means it's the initial state, or we've only seen zeros so far. State B means we've seen a 1 in the previous clock cycle, and state C means we've seen 2 1s in the previous 2 clock cycles. This is a Moore type state diagram, and we can tell that for a couple of things. You can determine that from a couple of features. One feature is that the output is associated with the state of with each state in the diagram. And secondly, the transitions are labelled just with the input that gives rise to that transition. In contrast, when we'll see the Moore diagram again, recall that the Moore diagram associates with a transition, not just the input that gives rise to that transition, but also the output that you observe with that input. All right, so the output is associated with a transition, not with a state. Okay, so VHDL code for the Moore type finite state machine. Unfortunately, there's no standard approach to describing these finite state machines, so we're going to go through a number of different ways of doing it. They're all very closely related though. So it might look a little overwhelming initially, but it's really relatively straightforward. The main feature is that we define what's known as an enumerated type here. The state type, that's our name, has the values A, B, and C, and then we can declare a variable, a signal, to be of type state type. All right, so there's only 3 values that state type can have, A, B, or C. This big process that we then hear implements the entire state diagram, apart from the output logic, which is right at the very end here after the process is finished. So it's a process that has an asynchronous reset, as you can see up here, but otherwise it's synchronous. It's only got clock on the sensitivity list. So if the asynchronous reset is active, i.e. reset n, meaning the n meaning active low, which is just a convention, if it's 0, then set the state of the machine to A. Right? That's this arrow that comes in at the top here, the reset taking us to state A. Otherwise, if there's a rising clock edge, if clock tick event and clock equals 1, then depending upon the current state, Y, then we're going to do a number of different things. So if we're in state A, if the input is 0, then we're going to stay in state A. Otherwise, enter state B on that rising clock edge. Similarly, if we're in state B and we get a 0, we return to state A. But if we get a 1, we'll enter state C. And in state C, if we see a 0, we'll go into state A. Otherwise, we'll stay in state C. All right? That describes exactly that state diagram, right? Finally, the output is 1 when we're in state C. Otherwise, it's 0. So the output logic's really very straightforward here. So what's special about it is that we have this enumerated type. The compiler therefore chooses how many flip-flops it's going to use. That's not given by the state type, although one might see there's actually a number of different ways of encoding this. I'll talk about it a little bit more and you'll see it in the lab. So the compiler chooses the number of state flip-flops and changes it in state occur on positive clock edges here in this very large process that sort of combines the next state logic together with the flip-flop logic, right? Because this big case statement is really taking into account what state we're currently in and determining what the next state should be as a consequence of the input. Are there any questions about this? Does it make sense? I see one person nodding. 2 people nodding. Good. All right. So here's a simulation that was done on that logic. This signal Y is actually the current state, so you can see it changing from A to B to A to B to C to A, B, C, A, right? The reset N is 0 initially, so that forces the machine into state A, and then it's 1 beyond that. We see our clock signal here, and we see the input W, right? Now, W goes high just after the rising clock edge here, and it's high while this rising clock edge comes along, and therefore the machine enters state B at that point in time. Since the next rising clock edge sees W being low, the machine re-enters state A, but on the subsequent rising clock edge we enter state B, and since W is still high on the active clock edge after that, we enter state C, and as soon as we enter state C, we see Z going to 1. Of course, on the next rising clock edge, W is 0, therefore the system resets to state A. Next rising clock edge takes us to state B because W is 1. Since W is still 1 on the subsequent rising clock edge, we enter state C, and we stay in state C because it's still 1 when the next rising clock edge comes along. But the final rising clock edge that we see here sees W equal to 0, and therefore the system resetting back to state A. So it's doing exactly what we want it to do. It looks like it's perfectly simulated what we want the machine to do. Right, the point's made here. This is a simple finite state machine. The ones you'll look at in the lab, certainly until the very last lab, are pretty straightforward, so it's easy to use a simulation. The very last lab has a fairly long simulation involved to prove its correctness, but it's reasonably straightforward still. More complex systems are going to need much more sophisticated acceptance tests in the simulation. All right, one alternative for specifying the finite state machine introduces a second signal so that we have not just the present state, we also have the next state. This then allows us to more explicitly model the next state logic that we saw in our very first model of the finite state machine. Let me remind you of that model. So this one here, where we have some next state logic that takes the current input and the present state and determines what the next state input should be to our flip-flops. We have our state flip-flops, and we have output logic that depends either only on the present state or on the present state and the current input as well. So going back to where we were, we see now a combinational process. This doesn't have a clock in the sensitivity list, so this is combinational, which requires simply that every signal that's on the right-hand side of an assignment statement is in the sensitivity list, as well as any signal that is part of a conditional expression, like the Y present here, right? So this is the next state logic that determines what the next state input to the flip-flop should be. Over here we have the state flip-flops being realized, which assign the next state to the present state. And finally we have the output logic down the bottom here, which really just defines the output in terms of the present state for this Moore machine that we see. So what's happened here is that we've separated from the previous design, which combined the next state logic and the state flip-flops in one process. We've separated that out into two processes, and some people prefer it that way. They prefer to see this combinational process that defines what the next state should be, and then have an explicit process for assigning that next state to the present state on a rising clock edge, or to reset the machine, and finally to have the output set. Okay, so this is quite common as well. We're still using an enumerated type up here, so the possible values for y present and y next are just A, B, and C. This is just a symbol. It doesn't tell you how many flip-flops are being used. That's up to the compiler to figure out and to implement. All right. So if we just left it at an enumerated type, it'd be up to the compiler to figure out how many flip-flops it's going to use. And I think for Vivado, the default will be that it's going to use a one-hot encoding. What does that mean? It's actually going to use 3 flip-flops, and it's going to have the first one active for state A, the second one active for state B, and the third one active for state C. Why does it use one-hot encoding rather than a binary encoding as we've been using? Any ideas? Might not be obvious. It's using more flip-flops, 3 rather than 2. That's not a huge difference, particularly when you have thousands of flip-flops on the FPGA. So that's one reason why it doesn't come with a high cost. But the benefit, you were going to say something? Sorry?
It's faster to read the one-hot which
Mm.
the machine is in rather than decode the binary back into.
That's right. You don't have to have this decoding logic to figure out how should you be mapping from a particular state to particular state variables. You've only got a shift register effectively that you're moving states between. So the logic is simpler, and as a consequence, because the logic is simpler, it requires less hardware, and therefore it's faster. Okay, so that's another benefit from that. But let's say you did want to enforce your own encoding. Then in Vivado, this is what you'd have to do. In different CAD tools, there might be a different way of defining how you use your own encoding. So this is really up to the tool vendor to define how they would override the default being chosen by the tool vendor anyway. Okay? So this is not necessarily the same for different CAD tools. And you'll be looking at a specific way of overriding the encoding in the lab as well. All right. There is a way, though, that is constant for all VHDL compilers, where it doesn't matter who the tool vendor is, and that's to declare a constant for each state that you want to identify. So here we're declaring that A is really just a standard logic vector, 2-bit standard logic vector with the value 0, 0. B is a 2-bit standard logic vector with the value 0, 1, and C has the value 1, 1, right? That'll work in any VHDL compiler. The impact of that, because we're now using standard logic vectors, when we come to our case statement here, we can't rely on the fact that we've only ever got states A, B, and C. We've also got the possibility that this standard logic vector that we're checking out, y present, which has got to be a 2-bit vector, might have, well, 78 other values, right? So we have to have a when others down the bottom here to catch all of those non-standard or non-isolated, non-defined states, okay? So that's a consequence. I wouldn't advocate ever really writing VHDL this way. It becomes far more wordy. It's unnecessary. The tools are good. Let the tools do their job. Let them do it as well as they can. Depending upon what the target is, they will find the most effective way of implementing the code. Right, what about our Mealy finite state machine? So here we see the Mealy machine that we had before, and I wanted you to think about it in contrast to the Moore machine. The output is now not directly associated with a state, but it's related to a state that we're in, plus the input that we're getting in that state. So if we're in state B and we get a 0, the output's 0, and if we're in state B and the input's 1, we get a 1 as the output. Right? That's the distinguishing difference between Moore and Mealy. Moore has the output associated with the state, Mealy with a given state and a particular input in that state. Therefore, the transitions have to be labelled not just with the input that gives rise to the transition, but also with the output that is observed in this state with that input. Right. What's different in this guy? Well, we've again got a combined process here that takes both the next state logic and the flip-flops in one go. So this is our synchronous process with an asynchronous reset, setting the machine into state A, given that the states are enumerated and we only have two of them, A and B, and we only have one state variable, Y. But there's a second process in this design that's been defined for the output logic. It's probably a bit of an overkill. It's not really necessary to have a process to do this because a gate would have probably been enough. Well, we need to know what state we're in, but you could have written this as a single select statement still. So here it's a combinational process that's dependent upon the current state and the input W. If the current state is A and then the output is 0, but if we're in state B, the output is the same as the input W. Okay, so we could have just said Z is W when Y equals B, when Y is B, else 0. We didn't have to write a process for this. But it's common to have a process for the output. It's also common to split this process into two. And so for Mealy machines, we often see three processes in the description. The next state logic, the state flip-flops, and the output logic. 3 different processes. Are there any questions on this? Good. Seems like I've managed to convince you. Here's the simulation of that design. Now, this is a little tricky. Here we see the input is just slightly delayed from the active clock edges. So W becomes 1 just after the rising clock edge here, and therefore, given it's active for a whole clock period, it's high when the next active clock edge comes along. Therefore, we enter state B, and because the input is still high for a short period after that active clock edge comes along, we see our output glitching, right? On the next active clock edge, the input's low, and therefore we see the machine resetting to state A. The input is high on the next rising clock edge, therefore we enter state B, and shortly thereafter, Z will go 1. When the next active clock edge comes along, we're still high, and so Z is still 1 for a little while after that active clock edge, while the input W is still high and accounting for the propagation delay of the AND gate. And it's the same story down here. So does this glitch matter? Should we worry about it? Well, if this is a controller, let's say this clock is running at 100 megahertz, we're not going to see it as humans as a flashing light or anything like that. What we have to worry about is any other circuit that's looking at the output of this circuit and making decisions on the basis of that. So if Z is high for a very short period of time, what we have to worry about is that Z being high, is that detected by any downstream circuit that's making use of that output. And for that to be even seen by that circuit, it sort of has to coincide with a rising clock edge. Now, if the clock edges are coinciding, if they're happening at the same time, the downstream circuit isn't going to see a rising clock edge until here, and by then Z is long gone low, so it doesn't really matter, right? Whereas over here, we get a rising clock edge, Z's 1, so any downstream user will see that Z. Same here, rising clock edge, Z's 1. Same here, rising clock edge, Z's 1. So it's for 2 periods there, which is what we expected. So that all looks fine. It becomes a little bit more critical when that offset between when there's a change in the input and when the clock edges come along happens. Here I've shifted the input by half a clock period. Now the input rises on falling clock edges, and so you see a slight additional delay. So the rising clock edge happens right in the middle of the period while our input is high. So we see here, for example, that we enter state B and immediately we have our input Z going to 1. Similarly over here, for sort of 1.5 clock periods, Z is 1, and for here, 2.5 clock periods, Z is 1. So is that a problem? Well, not if any downstream, so the problem here is that W was only 1 for 1 clock period, and yet for half of that clock period, the output is 1 as well. So it's not really behaving as it should be behaving. It should not assert the output Z until the next clock edge or the next clock period. But that's the fault of this asynchronous input and the shift in time that it's there for that makes the Mealy machine now not behave quite as nicely as it should. Is it critical as far as the downstream circuit is concerned? Well, there's no actual rising clock edge here. So we get the rising clock edge, and it's only after the rising clock edge that the machine enters state B, and therefore only after the rising clock edge that the output Z goes to 1. And so any downstream circuit that's synchronized with the same clock isn't going to see Z being 1 there. By the time it goes low again, we're still on a negative clock edge. That doesn't really matter. Similarly, here, it's not until this rising clock edge here that any user circuit would see the output Z being 1, right? And by the time the second one comes along, it's 0 again, so we really only see or read one Z equals 1 clock cycle, whereas here we'll see 2. We'll see one corresponding with this rising clock edge and one corresponding with that rising clock edge, which is exactly how we expected the system to behave anyway. So here it doesn't really matter too much. Okay? All right. Are there any questions? Why it glitches here? Well, recall that our design says if state is B and the input W is 1, then Z is 1. And here we've entered state B, and for a very short period of time, W is still 1. And so for that period of time, Z has to be 1. But as soon as W goes to 0, Z becomes 0 again. Does that make sense? Okay. All right. So, any questions? Any other questions? So I've sort of made a good start on this lecture, and I'll keep going on it on Friday, but there's a little bit of tidying up I have to do on lecture 5 still. So I want to just, if you feel tired now, I'm going to make you even more tired because it's pretty heavy going. I'm going to talk about timing parameters a little bit more because we didn't actually finish the discussion, and that will introduce another issue that gets talked about as well, but it's less than 10 slides, I think, from memory. All right, so this was our previous lecture just on flip-flops, registers and counters. And there was one topic that we talked about on Friday and we didn't quite finish it, the timing properties of synchronous components and circuits. And so that's where I want to pick up the story. So we talked about flip-flops having associated with them 3 timing parameters. The clock to Q propagation delay, which is the time that it takes for an input to be seen at the output after the active clock edge comes along, be it a falling or a rising clock edge, right? That was the propagation delay, which might be different for 0 to 1 and 1 to 0 transitions. There's also the so-called, so that's this guy here, between a rising edge here and the output going high in response to the input being high. There's also the so-called setup time. That's the amount of time that the input has to be constant for before the active clock edge, and the hold time, the amount of time that the input has to be held steady for after the active clock edge, for the input to be reliably seen and transferred to the output of the flip-flop. You recall those 3 parameters? Right, so we know that they exist, and we're going to make assumptions about how large they are in the next slide. So we're going to analyze this very simple circuit, simply a flip-flop with an inverter on the output feeding back into the input. So what do we expect that guy to do? Every clock cycle we expect it to toggle from 0 to 1 and from 1 to 0, right? And we're going to make the following assumptions: that setup time is 0.6 of a nanosecond, hold time is 0.4 of a nanosecond, and the clock to Q propagation delay varies between 0.8 and 1 nanosecond. We're also going to assume that a K input gate has a propagation delay of 1 plus 0.01 K nanoseconds. So as a single input gate like an inverter is just going to have a delay of 1.1 nanoseconds. A 2 input gate is going to have a delay of 1.2 nanoseconds, and so on, right? Very rough assumption, very first order sort of analysis. Now what we want to do often with our circuits is figure out how quickly can we run them at. So what clock frequency can we operate this circuit at? So we need to figure out what's the maximum speed we can drive this circuit at with it still operating correctly. So that requires us to figure out, well, what's the critical path in the circuit? Because we have to make sure that we don't exceed the constraint of the critical path, right? So in this case, we want to know, well, what's the maximum amount of time between an active clock edge and a change in the input here? Because we can't clock it any faster. If we clock it faster than that, we'll never see changes in the input, and it won't toggle. It will just stay at 0 or just stay at 1, right? Because it won't have seen any change in the input, because there won't have been enough time for the circuit to compensate for the clock to Q propagation delay, the delay of the inverter, and the setup time of this flip-flop. So if we want to figure out what the minimum period or the maximum clock frequency is for this circuit, we have to figure out what the critical path is. And in this case, it includes the maximum clock to Q propagation delay plus the delay of the inverter and the setup time of the flip-flop. And when we add all of those parameters up together, we get 2.7 nanoseconds, and the reciprocal of that is 370 megahertz. We can operate it at any frequency less than 370 and it's going to work fine. But if we try and operate it at faster than 370 megahertz, we're not giving signals enough time to get back to D and to influence D, right? We're not going to be satisfying setup time. And so it may not toggle correctly. If I try to operate it at 500 megahertz, it's not going to work at all. Okay. We also need to check that we're satisfying the hold time. So we've checked that we've satisfied setup time. And to do that, we need to figure out, well, what's the shortest possible delay between an active clock edge and the D input? Because we want to make sure that D is held constant after an active clock edge for long enough to satisfy hold time. So we don't want to change due to that inverter. So we consider the minimum possible clock to Q propagation delay plus the delay of the inverter. And when we add the two of those together, we get 1.9 nanoseconds, and that is much greater than 0.4 nanoseconds the hold time. And therefore, we know signals can't get here fast enough to interrupt the hold time. All right? So it's going to work fine. So we're going to do this analysis again for a slightly more complicated circuit. We saw this 4-bit counter previously. This one's just an up counter. It has an enable. The exclusive OR on the D-type flip-flop just makes sure that each flip-flop's operating as a toggle flip-flop. So now the longest path is, well, the clock to Q propagation delay on the least significant flip-flop here, the delay of this AND gate, this AND gate, this AND gate, this exclusive OR gate, and the setup time on this flip-flop down the bottom here, right? So it's a much longer critical path length here. In this case, that adds up to 6.4 nanoseconds, and that means we should be able to operate the circuit at a maximum clock frequency of 156 megahertz. In fact, this is probably being a bit too precise. Since these numbers have all got only 2 significant digits, we probably should say any faster than 150 is possibly going to be problematic, right? Okay. This is an important caveat. We're assuming here that the enable signal's well behaved and that it doesn't toggle at some stage to upset the apple cart, so that, you know, setup time isn't satisfied down the bottom here. We'll have a little think about that in a moment. The shortest path from a clock to a D input is from this guy here through the AND gate, through this exclusive OR gate to this guy here. So we have then the minimum TCQ, which is 0.8, plus the 1.2, sorry, I forgot about the shorter is the path just from one flip-flop output to the input. That's 2 nanoseconds, which is obviously much greater than 0.4 of a nanosecond. So this path here takes 0.2 nanoseconds, takes 2 nanoseconds to get to D. The hold time's only 0.4, so we've clearly satisfied the hold time. Assuming enable is well behaved, right? Because it could be that enable gets changed at a bad point in time, and that means D gets upset much sooner than the 0.4 nanoseconds. So I keep talking about enable being well defined. When is it best to deassert enable here? Or assert it? And maybe you should think about, well, what happens if the enable signal and the clock signal are sort of synchronized? So let's say the enable changes at precisely the time that the clock signal changes. Is that going to cause us any problems? Sorry?
We want to satisfy the setup time.
Well, not on the first clock cycle, but it definitely will be satisfied for the second one, right? Other than that, is that acceptable? So if enable changes at time 0, there's a latency of 1.2 nanoseconds before it's seen by D, and it has to be set up for 0.6 of a nanosecond, wasn't it, the setup time? Yeah, so 1.2 plus 0.6, so 1.8 nanoseconds. Given that the clock period is 6.4 nanoseconds, that gives us plenty of time for it to be set up here, okay. What about down the bottom? We've got 3 AND gates plus exclusivable gate, that's 4.8 nanoseconds plus the 0.6. We've still got plenty of time for the lower one as well. So coordinating the enable with the clock seems to be fine. So changing it at 0 time seems to be acceptable. But how far can we go before the clock edge arrives, and how far can we go after? And that's a question we'll look at in the exercises for this week, or for next week. No, it'll be this week actually, because this was last week's lecture. Now that raises another point that I do want to just touch on. Not that there's too much analytical stuff that I'm going to ask you to do or anything, but I want you to be aware of it. Clock skew is the spread in time in clock edges arriving at the various synchronous components in a digital circuit. How big's a chip? Big chips are several centimeters wide. How long does it take for a signal to cross that width? A couple of picoseconds at least. It's not a few milliseconds. I think a nanosecond's 30 centimeters, right? So it should be something like, yeah, a couple of picoseconds, maybe 10 picoseconds, as much as 10 picoseconds. So there's a spread. If we initiate a signal at one side of the chip, by the time it gets to the other, that's several picoseconds later. So FPGAs and many chips have special clock distribution networks, sort of H-tree-like clock distribution, where the clock source is in the center of the chip, and then it's distributed in a balanced way to all sectors of the chip, and that minimizes clock skew, okay? So let's just think about our counter again. Let's say on the less significant 3 flip-flops, we have this timing graph, but for the most significant flip-flop, it's delayed by 1.5 nanoseconds. So there's a 1.5 nanosecond skew between the most significant flip-flop that was down the bottom and the ones that were above it in the diagram that we looked at. Then the effect of the clock skew is to shorten the critical path length as far as that D input is concerned, because we've actually got additional time available for the circuit to settle before the clock signal comes along for that particular flip-flop. So it has the effect of reducing the overall critical path length as far as that flip-flop is concerned. But now the critical path length is actually on the path from Q0 to Q2, which is longer. It's 5.2 nanoseconds than the 4.9 nanoseconds that we derived for the skewed flip-flop. And so we still have to be careful about how quickly we toggle this counter. So we see that, we see the positive clock skew has the effect of reducing the critical path length and therefore relaxing some of the time constraints. On the other hand, a negative clock skew, clock signals arriving earlier at some points than another, give rise to a lengthening of the critical path, and therefore we have to reduce the maximum clock frequency. As far as hold time is concerned, if we have a clock skew, then that adds to the hold time requirement. So if we have for our Q3 a positive clock skew, then the hold time increases to the hold time plus the clock skew. And so now we have, for our shortest path, the AND and the OR gate from Q2 to Q3, plus the clock skew, it's 1.9 nanoseconds. It's still much greater than the hold time, so there's no violation. But we could keep on increasing the clock skew to up to 2.8 nanoseconds and not violate any hold times. But if we go beyond 2.8 nanoseconds, then we're violating the hold time and the counter is not going to be working at any clock frequency. Just won't work. So the main message is to design away clock skew as much as possible. You do not want to introduce clock skew. And where that is practically seen by you guys in the lab is you should never, for example, add additional delay or additional gates into the clock signal for any flip-flop. Always have just a pure clock signal going into a flip-flop. Rather than controlling the clock to control whether a flip-flop operates or not, you should do that synchronously on the input, on the data inputs, and control the value of the data input, not whether the clock is working or not, because that will introduce skew. Okay, so that's covered those slides that we missed. Are there any questions about what I've just talked about? Okay. You're done. You've got a 10-minute early mark. Thank you for coming and paying attention. So I'll see you on Friday. And if you're not here on Friday, I'll see you in 2 weeks' time when we have a quiz in this room at 12. All right? Very good.
Thank you.
No worries. No worries, Zane. See ya.